Okay, so welcome everyone to our first Waning Winter Wednesday webinar. Unfortunately, winter is not waning quite quickly enough in my part of the world here. Ottawa is still in the throes of winter, it feels like, so I hope it's more waning where you are. I'd like to thank you all for joining us. I know it's hard, it's tiring, and you guys we've been through a lot in the last little while, so hats off to you for being here this evening. Stephanie's our first in a series of 3 of these Wednesday webinars. Next week we have Paul and Anthony that are going to be doing some fun stuff with the microbit with us, and then the following Wednesday Chris and Therese are going to lead us in building a musical instrument with motion sensor, which is very cool. So over to Stephanie MacKay joining us from Edmonton, Alberta. And what's the weather like out there today?
Oh, hi everyone. The weather in Alberta right now is gray and trying to snow. So winter isn't waning just yet. It's hanging on. Yeah. So welcome everyone, and thanks for taking your Wednesday night to spend some time with me. And the topic that we're going to look at today is figuring out ways to build algebra confidence in all our learners, whether you are in a de-streamed course, such as what's happening in Ontario, or if you're anywhere else in the province where we don't have streaming anymore. We're keeping our options open for all. A lot of this learning that we've had in COVID, we do see a little bit of loss of learning, or students are just not up to par where they have been before. So tonight's presentation is trying to find ways to help these students out. We've got a little bit of pedagogy for you, and also ways that we can use the TI-83 and TI-84 calculator to help these students in a very non-threatening way, because we believe that all students can be successful math learners if we can build a good foundation. So to start this off, I'm looking at some of the social emotional learning skills that we have in math. This is new to the Alberta curriculum, but you know what? In a lot of our curriculums in our provinces, we have that belief as well with the social well-being of students, and also helping them build that confidence. Because when we build that confidence in math, we help students be capable math learners and make them feel a little bit happier about being in a math class. So part of my presentation tonight is about how we can make these connections in math every single day and every single lesson and straight or bring that across from lesson to lesson and day to day to give those students some confidence and help them be capable in math. It's allowing them to take some risks in a low stakes environment where they can learn from their mistakes. And it's also very private to them. Some of the assessment strategies that I'm going to share with you tonight, students don't have to share with the whole entire class, is very private to them, and they can take those risks and hopefully build a bit of confidence. Also, some of the ideas I'm presenting tonight, have the teacher intentionally build concepts from a very low floor to a high ceiling and however far you want it to go. And we're going to use the calculator today, not to do the calculations and not to do the math. We're going to use this device to draw attention to the mathematics. And this last part that I have is very important. I think when the practice of math is followed by an absence of practice, what happens is the memory of that math fades. And students could have intermittent recall or even false or part memory recall of the math facts. So some of the techniques I want to show you today is just a quick little formative assessment. What do the students remember? Do they really understand the math? Do they really understand the definitions? Because math is made up of a lot of different symbols and a lot of different definitions. And you know what? Those are the foundations of the mathematics. And if students aren't understanding the definitions, and if they aren't understanding the notation, well, then how do we build that foundation? So again, a teacher can teach something and then a week later, if that concept hasn't been practiced, students might not remember it in its entirety. When we think of exponents and power laws, students might have been exposed to those exponent rules in a previous grade, but then all of a sudden, the next year, the teacher might think, oh, you already know the exponent rules, but they might know them part way. So we're going to take a look at how do we use the calculator to bring some of those memories and test for those false memory, or try and reinforce good mathematical definitions and math notation. Now, before we jump into the math, I want to do something with definitions. So I want to reveal a word to you. And I know all of your mics are muted, but I want you to say that word out loud. I'm curious to know how you pronounce that word. And I'm curious to know how you would use that word in a sentence, or what definition of this word you were thinking when I presented it to you. I was just wondering, were you thinking lead, like a teacher leads a class? Were you thinking, hey, she took the lead and won the race? Or I wonder if some of you pronounced it differently. Did you say lead, as in a pencil lead? So within this English language, the word lead or lead, I mean, it's spelt the same, but it's got different meanings depending upon the context. So interesting about how I want to do this with math, because math, I'm going to start with this simple symbol. And I'm going to name this symbol, I'm going to call it a dash. And I want to, first of all, explore the different meanings of this dash, and maybe what some of our students see when they see this simple dash. So first of all, I'm going to take that dash and put it between two numbers. And when I put it between two numbers like this, the context, I think, means subtract. And we would say 5 subtract 3. And then we get a result. But wait, did you notice this symbol right here is made up of two of these dash symbols parallel to each other? And when two of those dash symbols together like this are put together, it means addition, or addition, it means equals. So 5 subtract 3 equals 2. Again, it might be important to point out that simple dash shows up in lots of different ways. And we might then present something like this: 3 minus 5. What? Did you notice that? First I said 5 subtract 3, and then I said 3 minus 5. So even though that dash symbol is in between two numbers, it can be spoken in different ways. So I'm thinking of our English language learners, that they have exposure to all the different ways that we talk about that subtraction or minus. So we've got 3 minus 5, and the result in this case is dash 2. Now we call this a negative 2. Oh my goodness, that's confusing already. First it's subtract, then it's minus, and now it's a negative 2. Look at that context that we have to be aware of for that simple little dash symbol. Then we start working with this dash symbol, and are we allowed to put these two dashes beside each other? And I'm going to read this as 3 subtract a negative 5. Yeah, we're not allowed to do that. That's bad math notation. So now all of a sudden, when we put those two dashes, those two dashes together like that, we have to use parentheses when we're talking about 3 subtract a negative 5. So again, this notation is hugely important when we're working with students, so that they have that root or that foundation in reading the math and understanding what's going on. I want you to take a look at the result over here. Did you notice that this addition sign is two of these dash symbols perpendicular to each other? Lots of different places it's showing up. Here's another example where the dash shows up. And in this case, it's between two numbers, but they're stacked one on top of the other. And this means a fraction bar, and the operation now becomes division. So and division also could be written with that dash and two dots, one up above and one down below. So look at all the places where I'm finding this dash symbol being used in mathematics. And I'm not even going to get into that -1/2 equals, do we put the negative in the numerator? Do we put the negative in the denominator? Or do we put it out in front? So again, a little bit of notation and a little bit of understanding, certainly for students, that all three of these mean somewhat the same value. And then once we get into higher level or other concepts and we talk about exponents, now we've got this dash symbol next to this little number 1 in this exponential notation, or in this power. And in this case, that dash doesn't mean add, it doesn't mean subtract, it doesn't mean a negative number, it doesn't mean divide. It now, and the negative exponent means take the reciprocal, and we get that 1 divided by 2. So I used to do this a lot with my grade 10s, and just recognizing where this dash symbol shows up. And then a little bit more in our Alberta grade 10 curriculum, we've got some of this notation, or I guess this is more grade 11, where we've got this notation where it means, well, it no longer means take the reciprocal. This now means take the inverse. And at our grade 12 level, that dash symbol working with these function notations means take that inverse. And then also that dash symbol means transformations of graphs. So that simple little dash in math has a lot of different meanings depending upon the context. And what I have always done to help those low-level students is just to bring up the meaning of that dash symbol in whatever context it's in, especially when we talk about reciprocals and inverses, whether it's in exponential notation or in function notation. And when I taught that class, I did bring in the dashes in all its different places that students would have seen it before. So hopefully that was helping my students get an idea of being aware of the math notation and the definitions of what that symbol means. So the next part that I want to get into is dealing with powers and exponents, because exponents isn't, it is in the math grade 9D streamed for Ontario, but let's face it, exponents and powers are everywhere. And depending upon the different levels or the different course, you either start with exponents as an introduction or you build upon it in a later year. Now, when I teach exponents, with part of this building confidence in all of our math learners, I wouldn't start with exponents right away. I often started with something like, what operations do you see? And before I go any further, did any of you notice I've got bad math notation? And now you're wondering where. Maybe some of you know where my bad math notation is. My bad math notation occurs with this equal sign, because when we're talking about equals, an equal sign is not an operation. It's a relationship. And it's a relationship between a left side and a right side, or a quantity on the left side and a quantity on the right side, that they are equivalent. So to help my learners understand equality, I would never represent this statement with a blank on the right side. I would put something in there. It doesn't have to be a variable, because sometimes variables are scary depending upon the level of the learner. I would either put in a blank space, or a little space, or even like a symbol like my rectangle that I have here, to show that I've got a left side equal to a right side. And so now, once my notation is correct, I'm not asking about what the answer is. I would first of all ask, what operation do you see? And hopefully the students would say that they see subtraction and they see multiplication. If you wanted, you could talk about order of operations, or you might leave that for another day, depending upon what you're leading into. I want to talk about exponents, and I want to talk about what operations you see. So I would leave the order of operations till a little bit later. And in this case over here, students would recognize they see division and they see addition. And then I start making it a little bit more difficult, taking it up a level. What operations do you see? Hopefully students say that they see addition, but then I also want them to say that they see multiplication. And then hopefully they also recognize that the parentheses mean a grouping, that something is being grouped in the math. And then I can take it to exponents. What operations do you see? Hopefully students say, oh, we see division. That's the obvious one. But now, what do we see here? And students might say they see a power. That's a label, though. That's not an operation. Students might say, oh, we see an exponent on a base. Well, that's a label. That's not an operation. So what operation do they see? Hopefully they would say they see multiplication. And then I can introduce my exponents and my powers with understanding that the exponents mean multiplication. By talking about what operation do you see, I'm doing
I
a
can
form.
challenge you on that a little bit, Stephanie. Go back to the previous slide for a second.
Mm-hmm.
So this is interesting. So, I mean, the move in elementary from addition to multiplication, seeing multiplication as repeated addition, right? And then moving from multiplication to exponents, like this idea that exponents kind of somehow represent repeated multiplication. What if it was 2 to the exponent 1.2?
Well, then our rule breaks down, doesn't it?
I just say that because it's funny, because I would suspect that everyone on the webinar tonight, when you introduce kids to the ideas of exponents, and again, I'm not sure kind of the context in which it arises specifically in your curricula, but probably you're leading to some laws of exponents or something like this, right? So it's interesting how you're phrasing it though, like this idea of looking for the operations. And so on. Yeah, and that's one of the interesting things too. The language that you use, how well does it carry over to when you get into these? Oh my God! Now the exponent's 1.2. So is that image of repeated multiplication? Does it move along with you? Well,
And if a student asked me that question, I would have a good answer, in the sense that initially, if we had that, 2 cubed is 2 times 2 times 2. So that definition of repeated multiplication works. But then as soon as we get 2 to the exponent of 1.2, then it breaks down, because that exponent then can be worked in a different way. Or that's where we would have that higher level of thinking,
or
because
even the idea of the negative exponent, how does it fit into that framework of repeated multiplication, right? So
right.
there's some
So
interesting. Sorry, I
so
didn't mean to be a wrench.
no.
I thought that was an interesting thing to think.
But definitely, I think it's important to have those conversations, because you are starting at the base. And often when students are first exposed to exponents, they do talk about the repeated multiplication. And then let's take it beyond, because in math, we can take it as far as we need to take it. And no longer do we need to hang on to that original definition of an exponent, because we have a powerful calculator to calculate 2 to the exponent of 1.2, because we can't really do that in our heads, unless any of you can. I don't know. But thanks for that, Tom. What I was working towards was giving this formative assessment, talking things through, and helping students become successful in the understanding of the notation before we jump to the rules. So giving that frequent opportunity for a low stakes assessment, and understanding the notation and understanding the definitions of the math. So now I'm going to take a look at the powers. And again, this is at a low level. It's developing the idea of exponents as repeated multiplication, and not going into Tom's crazy world of of irrational or rational exponents. But very simple when we're talking about 5 squared and we're trying to develop or form this foundation of understanding, we might ask students to explain the significance of each numerical value. And the most often case that we get, ooh, did you see that answer that we got? Hey, that's awesome. From Maria, that's awesome. That makes sense to me. And it'd be interesting to get students to prove that. Thanks for that. With this one, explaining the significance of each numerical value, I often get students who give the answer, well, 5 is the base and 2 is the exponent. But that was the label. I'm wondering, what do they do? And here's where I'm going to introduce the calculator. And the keys on our calculator, and I'm going to show you the TI-84 Plus CE emulator soon, but the keys that are hidden on the calculator that not many teachers use is this equal sign. And we can find that equal sign by pressing second function math. And I want to show you how I would use this. So here's my emulator. I would have the students type in 5 and then squared, and I would get the second function math and pull up that equal sign. And talking about the function, what are the functions or what are the significance of the numerical values and what do they do? And students might say that the base is 5, so that's the number being multiplied by itself. And then the function of the exponent in our introductory definition is the number of times you multiply 5 by itself. Now I've got an equation in here where I have a left side equal to a right side. And notice what happens when I press enter. I'm not going to get the answer 25 because we're not doing a calculation. What we're doing is we are showing a left side equal to a right side. So these two notations are equal to each other. Now, this one, anyone understand? Does anyone know where this 1 is coming from or what this 1 is representing? Do you know what the calculator is using or what logic they're using? I'm going to go ahead and say, hopefully you guys said that it's true. Binary, so 1 equals true. What letter would, or what would be used for false? What do you think would happen if we had a false statement? Yeah, a 0. And this is our Boolean logic or our binary logic where a 1 is true and a 0 is false. Or, hey, if it's a true statement, you got 1 point. If it's a false statement, you got 0 points. So you can have students go to those foundations of their understanding. And did you notice that a student could do this on their handheld and nobody else is watching and they would get results immediately?
So students can put in 5 squared equals 5 times 2. So 5, 2 kind of is 5 times 2, which is what a lot of kids do. What did you just do right there? That's cool. Did you copy and paste?
I did. So to copy and paste, I can press my up arrow, up arrow, up arrow, and then see how it's highlighted, and then just press the enter key and it pastes it down into a new entry line. And then I press the left arrow to back up and I just changed that to a 2 and pressed enter. And now you can see that's a false answer. And here's where if a student is getting a 0 or a untrue or a false answer, I might ask them to play around until they get a true answer so that they can reinforce this means 5 times 5, not 5 times 2. Another example that I might move towards is this case right here. And I would have students type this into their calculator. So on the left-hand side, we would have 2. I put in the multiplication sign, 2 times 3 squared. And once again, I would go get that equal sign, second function, math, and get that equal sign. And here's where I would have the students predict not what the numerical answer would be, but what does the extended, what is really being multiplied here? And it's interesting because we might get some students who want to say the answer is 6 squared. And then when they press enter, they're going to see that they have a false statement. So now they can try again. by copying and pasting that down and backing their cursor up, and I can press the delete key to clear out some of those numbers that I don't want. I can delete that. And now students can type in, well, this means 2 times 3 times 3. So the significance of the numerical values, 3 is the base that's being multiplied by itself. 2 is the exponent that tells us how many times to multiply the base by itself. And then this other 2 is like a coefficient or just another number that we're multiplying 3 times 3 by. So hopefully by expanding this, students have a little bit of a better grasp of what the math means, because we get a lot of students here in Alberta that go, oh, this is equal to 6 squared, which is 36. But notice that none of the answers are showing up. I'm not getting 18 as an answer because I want to look at what's happening to the math and exposing the math rather than just jumping to an answer. So here are some other examples that I could have in this same idea. And with this first one, we could talk about, again, what is the significance of the numerical values, or I could even ask what's being multiplied. And I would have students purposefully put in the -2, put that parenthesis around, and now you're going to say, wow, pressing this into the calculator is a little clunky, but that's on purpose. It's on purpose to slow me down so that the students can process and understand the math. And by slowing down and putting those parentheses in, hopefully the students understand that this is a -2 being multiplied by a -2. And now when I press enter, I get a true statement. Now, when we move into this next example that I've given, which is -2 squared, I would ask students what's being multiplied by itself. And if students go -2 squared and then pull up that equal sign again and say that this is equal to -2 times -2, which is a common error that students make, they will get a false answer. So here they can go back and correct what is actually being multiplied. And here again, I would come and I would delete those, and we would have, if we want to expose the math even further, we can say that we have a coefficient, or we've got that extra number out in front. That negative out in front actually means a -1 times 2 times 2. Notice how that's similar to the example that I did a little bit higher up. Hopefully I can build some understanding with these students to break apart the math and see to which base that exponent is actually applied. And then here's another
Before you go on
situation.
there, Steph, that it's a really interesting thing, that notation of -2 squared meaning -1 times 2 times 2, and the history kind of books and typesetting. Like the reason why they didn't write -1 times 2 squared was historically it was expensive. Every character that you
Mm,
typed, so there was a lot of, let's assume there's a character here kind of going on. So there's invisible things that mean things a lot in math. So the idea that you write 2 and there's no exponent 1 in front of it, there's no coefficient of 1, but there could be, right? So I think that's really nice, kind of making the invisible visible for them there. That's a nice example.
Thank you. And this was also where I did that introduction with the dash, right? Where that dash meant a -1 times something, or, a -1 times a 2 to make it a negative number. So you can tie that in to whatever topic you're talking about. This next one that we had over here, how I would use this one is when I am teaching what that negative meant as an exponent. And it might have been something that we taught, and then a week or two goes by, and now we need to use it again or for review. And maybe as you're reviewing in your exponents chapter, it might be an idea to have students come back to this and see what their instinct is. To see, because lots of students see that dash in that exponent and think that this answer should be a -2. And here's where, again, I would get them to predict and maybe even predict the meaning that this means 1 over 2 squared. Just like that.
I'd be interested to hear in the chat, like how do you approach that transition from whole number exponents into even zero exponents and negative exponents? Does anyone have, how do you make that transition kind of from the meeting? Because Maria, you say fractions? How many of you do patterning stuff? Like, so the thing, again, just to play around with this for a second, can you just write 2 squared? And then we'll just want to, so just do 2 squared and then equals, and then 2 to the exponent 1. No, we won't do the true thing. I just want to, so this is where I'm kind of breaking down your model a little bit here. Just hit enter kind of thing.
Okay.
And then do 2 to the exponent 1. So if you were doing 2 to the exponent 4, 2 to the exponent 3, 2 to the exponent 2, and they see, oh, it's half of each of the previous values, right? And then when you get to 2 to the exponent 0, well, what's half of 2? It's 1. So that's one, rather than coming up with some magical, oh, it's exponent 0 is always 1. Well, why? And then what's half of 1? So 2 to the exponent -1. So that's, yeah, so I see that Anthony says, yeah, I like using patterns kind of thing. So that's an interesting way kind of getting at that transition of meaning too. That's a nice add-on to that for sure.
And then here's where we can do that. What was it, math fraction? So that's that pattern that you were talking about. I like that. Notice that I was using the up arrow to scroll up through my history and then further down. So lots of different ways that you can build that understanding and have students show that they know the meaning. The next example that I had over here isn't about getting a final answer. This one might be about, again, order of operations. So we could have a student entering 4 squared and then 4 squared and going ahead and getting that equal symbol and asking them to expand, what does this really look like? And they could do the 4 times 4 plus the 4 times 4. Again, breaking that apart and making the math visible and very apparent and very explicit. We could continue this by having the students go 4 squared plus 4 squared, and then they could do some mental math and they could enter this as 16 plus 16, and then they could get their final answer of 4 squared plus 4 squared equals 32. So that's one way that I could use this and talk about the meaning of this. But if I was building towards something like this and wanting to do this style of equation where we've got 2 times 3 squared minus a 3 squared, what I might want to do is have the students enter this as 4 squared plus 4 squared. And now we talk about like terms. And when terms are the same, what do? Well, we add them together. So that means that we have 2 of these 4 squared things. So kind of approaching something in a little bit of a different manner and bringing back that idea of coefficients, that you don't necessarily always need that coefficient in algebra, that you can do it with exponents as well and build some of that order of operations and other different types of levels so that students can get to this example here and be able to expand this, and again, not multiply the 2 times the 3 and recognize that this means a 3 squared or 3 times 3 and then times 2 or something like that, or that we've got a 3 squared plus a 3 squared and then we're subtracting a 3 squared. So maybe in this case, we can talk about subtracting 3 squareds and end up with a 1 3 squared. So lots of different ways that we can talk about the notation depending upon where you want to take the students. And we don't always have to stick to those traditional ways. Something else that comes up in the Ontario curriculum for grade 9 was scientific notation. And sometimes we've got teachers that are teaching scientific notation. I know I work with some science teachers, and they talk about moving the decimal to the right, moving the decimal to the left, and so on. And this is a quick way to have students check their understanding of how to move the decimal and how it affects that power on 10. So you notice that I typed in the 52.31 times 10 to the exponent of 5, and I used that equal symbol, and I would have students make a guess. What do they think the proper scientific notation could be? And they probably get this part correct, 5.231, but then let's pull up that 10 to the exponent of, and they can make a guess. Will this be to the exponent of 4, or should this be to the exponent of 6? And students, very much on their own, without any criticism from anyone else, can make a guess, make a prediction, and get an instant result. And that's what I like about using this equal sign, is that the students get that equal or that instant result. Because, and I'm just going to flip ahead, sorry, and then I'll come back to it. The idea with getting that instant result is that your body produces a little bit of dopamine, and dopamine is a feel-good hormone, and it gives satisfaction. So the more that these students, whether they're low-level students or high-level students, the more that they get satisfaction that they're doing something correct, when they make a prediction and it is correct, they get that dopamine happening in their body, in their brain, and it feels good. And then it also reinforces the memory so that you're building on these rules and building on this notation. So that's why I like using this equal sign when I'm working with students in predicting the results or what is their instinct when they are doing these calculations. Now, we were working with exponents, and you notice that I moved now into variables and working with exponent rules with variables. Well, we don't have a CAS calculator. This is a numerical calculator. It does algebra or it does arithmetic, but it can't do the algebra. But we can kind of make it into a fake computer algebra system by using the store key. The store key on our calculator is down at the bottom. It's next to the 12.3 or the 123 row. And you're going to notice what I did up here is I typed in 12.3, and then I used the store key to store that value of X. Oh, thanks, Shannon. I'm glad you liked my equal sign. Because again, it's a nice little formative assessment. So when we're working with variables, sometimes students get mixed up. So I'm going to show you how to do that with a fake CAS calculator. I'm going to type in 12.3. I'm going to use the store key, and I'm going to store it as the variable X. Now notice that you've got letters in green. You can actually store this number to any letter. I'm just choosing X because it's a convenient letter to use. When I press enter, now it's stored. And notice what happens when I select X and just press enter. X now takes on a value of 12.3. Now I'm going to clear that because I want to be in my fake algebra or my fake CAS world. And I want students to predict the answer. So we're going to type in X times X, and I'm going to use that equal sign again, and have the students predict what the expression should be. What should the right-hand side of the equation look like? And this is where students, you might get some of those students who think, oh, the answer should be 2x. Notice they got a false answer. So they can go back and you can ask them to correct their answer or correct what they think it should be. And now when they get in.
Can I jump in? So for those of you that are wondering, like what are the limitations of a fake CAS? What would they have gotten if they had assigned a value of 2 to X? They would have gotten a true statement, right? So that I think so there was some devious wisdom in Stephanie's choice of 12.3 as the value that she was assigning. So a really obscure value that won't accidentally be correct. Yeah.
Oh yeah, I picked 12.3 because it isn't a common number, and You know, I do this, I'm going to go off script right now because I use this when, what am I? I use this when we are doing things like x squared minus 4, and we're asking students to factor. And when we're asking students to factor, we might get a false positive if we assigned x to be a different number. So we know that the factors should be x plus 4 and then x minus 4. Ah, I went off script and I made a slight little mistake. Here we go. There we go. So in this case, when x is equal to 12.3, I get a true statement. But let's say we made x equal, oh, I did that wrong, to 2, and I'm going to store this in my x variable. And now we come back here and we're going to check this statement and we get a true statement. But what if a student made an error and they thought that the answer should be x minus 2 times x minus 2? They get a true statement, even though it's false. And I think this is what Tom was alluding to with me selecting that value for x to be 12.3. All of you understand that these factors are incorrect. And hopefully you can see they're incorrect because x took on a value of 2. And so here's where that fake algebra, that fake CAS calculator breaks down. It depends upon the value that you chose for x in order for the statement to be true or false. So that's why when I'm using my equal sign and assigning an actual number value to x, I'm going to choose something strange like 12.3. Hopefully that helps in some of your understanding. Did anybody have a question about that? Does that make sense to you? When I use this equal sign with my 30 level students or my grade 12s, and we're doing logarithms, I sometimes will use a negative value for x in a logarithm expression, and then they have to explain to me why the logarithm is coming out false or that it's not going to work. And so there we were very purposeful in selecting a value for x as well. So with just playing around with some of these different expressions with the variable x's, we can see that, you know, there's lots of different discoveries that you can have with common errors that students might make. Especially with something like this, students might want to add or multiply the exponents rather than adding them. And that becomes very evident when you put this calculator in their hand and they can check their answers. So I just had some other examples in here. We also could have examples where they're predicting the value of k squared when k was equal to -7, and have them predict lots of different results. And I think I had one other example for you, and that deals with algebra. And so working with algebra and algebra concepts, before I get into the algebra, starting from the foundations, I often talk about where are you counting and what are you counting. So in this case, when I have 2 plus 3 equals blank, I don't care that the answer is 5. I care about what are you counting? Well, what are we counting? Because back in kindergarten or grade 1, they were counting buttons or they were counting shoes or something like that. But when we have 2 plus 3, I guess we're counting whole numbers. And then when I look at something like counting fractions, I would ask, what are you counting? And the denominator reveals the size of something that you're counting, 1/6 of something, and where do you do the counting? You're doing the counting in the numerator. So then when we get into the algebra part, I do start with a visual. What are we counting? Well, we're counting daisies. Okay, we've got 6 daisies and 1 daisy, and that gives us a total of 7 daisies. And then when we move into the algebra For these low-level learners, they almost need this explanation that instead of writing daisy, we're going to put a D in there to represent the daisy. 6 daisies plus 1 daisy is 7 daisies. And the D just means that it has some meaning. It represents all kinds of numbers, but we do the counting in the coefficients out in front. And then we can move towards unlike terms. Well, what are we counting? We've got 4 ties and 2 frogs. These are not like terms, so we can't count in the coefficient section of the expression. So that's what we can start with and move towards simplifying to predict the results. A 3x plus 2 minus a 2x plus 1 equals, we can again use that calculator to have the students make that prediction. And I might even set it up where I would have them put the 3x next to the negative 2x and then plus 2 plus 1 and have them do the reordering to collect the like terms and then have them add together. So lots of different ways that we can use this calculator and that equal button and the stores and that store key, even with something like distribution or working towards distribution. Talking about x cubed, what did it mean? It meant x times x times x in one situation. What does 3x mean? Well, that meant 3 times x was x plus x plus x. And then I can move towards the distribution and have them describe to me, what does 3 parentheses x plus 1 mean? And hopefully students would say, well, that, if we've just done this last example, they would say, well, that's like taking x plus 1 plus x plus 1 plus x plus 1. And again, I would have students do this on their calculator to test their answers to make sure they're getting the notation correct. And here's where we start working into distribution. What do we really have? Collect your like terms. We've got an x plus an x plus an x. So we have 3 of these x's and 3 of the ones for a 3x plus 1 or 3x plus 3. And then we can also model that distribution, and we always do those arches, right? Or those little arrows, 3 times x and 3 times 1, 3 times x and 3 times 1 to get the 3x plus 1. Now, why would I do distribution that way? And this is something that Tom brought up when we were talking about exponents. What happens when this repeated addition breaks down? That's when we needed the understanding of that additional rule of distribution. Because the next example that I had was this guy right here. We don't have x plus 3 added to itself twice because that coefficient isn't a coefficient anymore. This is now another term. So here's where we can have the students practice with this distribution and multiply into the parentheses and predict the results. And again, as the students are building their competencies and feeling good about the math, I would have them deconstruct the mathematics before we just jump to those final answers. So those were some of the ideas that I had for using the calculator to help build confidence in math.
Go just back for a second to the previous slide, because there's even one other thing that, so on that second line, when you said, what does 3x mean? And you kind of got at the repeated addition, right? So that's assuming that they see multiplication between the 3 and the x, which not all of them see. So I think even another test of truth with the second math thing would be, is 3x equal to 3 times x, or is it equal to 3 plus x? Because it's not clear to everyone what that invisible operation between the 3 and the x is.
Yeah, so that, Tom, we came to the end of my presentation. And here's where we can open it up. We had students predicting results and getting even into more complicated expressions, just having them show the operations, having them deconstruct or expand before they jumped into doing all that algebra, just to build some of that foundation of their learning of math. So,
yeah, I love the comment that like, it's not, I never thought to use the calculator that way. When Shannon said that, I, I love that comment, Shannon, because that we hear that so often. So I've seen Stephanie do kind of a version of this session for pre-service teachers out in BC, for teachers out in Alberta, and you hear that comment all the time, eh, Stephanie? So people
Yes.
have a very fixed way they think of using this. I use it as a calculator and to graph, and that's it. So
Or
it's so refreshing to see that you can use this tool um,
to
in a lot more creative ways.
maybe to make the math a little bit more visible and not just always to go get the answer.
Mhm.
Um, and I do a lot of this even with when I'm working with radicals and the hidden numbers in radicals, that if you've got like the square root of 5, make that equal to, and then use the situation where you can actually put that index in using that other notation, put the index of a 2 in so that students can see that's the square root and it looks different than the cube root. So lots of different areas in our math curriculums that we can use just that equal sign or the store symbol.
And it even connects to those of you that have been part of the coding workshops that we've done. It's interesting how symbols mean different things in Python, for instance. So when you assign a value, that's a single equal sign, as opposed to a test of truth. If you want to test the truth of something, whether the left side is equal to the right side, it's 2 equal signs. So coding has its own little weird use of your little dashes, right, that are even different than this, that the kids have to get used to in Ontario, at least now as well, right? So,
Right. Oh, I like Anthony's comment. It's a truth checker. That's awesome. I like those. I'm going to use that.
yeah. And we can't or overstate, I guess, the importance of, like, this is a safe environment for kids to test their thinking, which is quite often creative, let's say, right? And they get feedback that's non-judgmental. And they get to kind of work through their, I don't know if we call them misconceptions, like their evolving conception of something, right? In a safe environment. That's so important.
What I find interesting is when you're the teacher at the front of the room and all the students are looking at their calculator, and it's so cool when they type it in and they get the wrong answer and that look of shock on their face. They were like, what? How's it the calculator's lying? And then they have to work through how to get a correct answer, and then it sinks in a little bit. I think having them get that incorrect answer almost reinforces it. They made that mistake. Now they've got to remember, oh, what did I do wrong? Which is a little bit more powerful than when the teacher says, no, you're wrong. So hopefully that was helpful for you tonight.
Was just a quick question. Was your genesis of using the 83, 84 like this, was it like you got to use the TI-inspired CAS, and then people that didn't have it said, oh, shoot, I can't do CAS? And then you having the aha moment of, oh, yes, you can. What was the genesis of it for you?
Well, for me,
Yeah.
well, we had the 84s before we had the Inspire, and I was doing this with the 84
Okay.
years ago. And then in my school, we adopted, or we took on the Inspire, and then I actually forgot about this, that it was actually on the 84 as well. And
Yeah.
so I'm glad it came back and remember it. Hey, Shannon.
Cool. So you were doing this well before kind of CAS was in vogue and everything,
Yeah.
eh?
Yeah.
Okay. Wonderful. Well, I thank you guys so much. And we were actually discussing kind of like, how long do we go with this one? But we really wanted this to be organic and respect the fact that you folks kind of are amazing for giving up an hour kind of in these crazy times to come out and enjoy us and to join us. And we're so appreciative of it. And we definitely rather end up on this side of the hour than that side of the hour. So Stephanie was very good about that. So thank you
Oh,
very much, Stephanie. That was really, really a wonderful. And it's always neat to kind of learn something and that you didn't, you didn't think was there. And then what we really hope is that you'll be able to take this back to your classrooms, right? So hopefully, and there's so many connections like this really, you just showed a little glimpse of how you use it, but the wheels were turning. You could see kind of with me and everyone else, like this connects to so many different places.
And I think also connects for all levels of those students, like whether they're struggling or whether they're high flyers. I mean, this is, I thought, was good for all of them.
Absolutely. So I thank you very much to Stephanie. Thank you to all of you folks for joining in this evening. I hope that you'll join us for the upcoming sessions too. They're very different, but again, what we're really doing is trying to get people to think in different ways and think about how they use tools in different ways, be a little more creative. So hopefully kind of that achieved that. It definitely kind of came across wonderfully. So thank you very much, Stephanie. Thank you all. Have a lovely evening still. Stay safe. May winter wane wherever you are quickly, and we'll see you next Wednesday. Thanks.